In order to understand stars, we really need to understand hydrostatic equilibrium very well. So what is hydrostatic equilibrium? It's basically where you have a direct balance between weight due to gravity and pressure in a gas. What you need is to have the outward pressure that is due to the gas pressure is balancing exactly the weight of the material. So there's an exact balance between the gravity and the pressure. This is something that has to be fixed in order for the star to be stable, and it is uniquely going to determine what the interior structure of the star is. And it's because of this requirement of balance between pressure and gravity that we don't find stars all over the Hertzsprung-Russell diagram, and that the main sequence is the place where we have this stable region, and that's because that's where this balance is met. So, at equilibrium, we have a balance of forces. You can think of it as being there's pressure in all directions from the gas, but there's only a weight towards the centre of gravity. So here we have a slab of material inside the star. It's got a weight acting downwards, and it's also got pressure from above the slab and pressure from below the slab. Now, because it's got pressure from above and weight, in order to balance, you're going to have more pressure from below. And what that means is that the pressure below is always got to be higher than the pressure above. So the pressure goes up with depth or down with altitude. Let's think about this a little more mathematically. Here we have a slab. It's a slab of material that's part of the star. It has a thickness delta R and an area across its base or top of A, and it has a density rho. There's a gravitational force acting on it due to its mass pulling it downwards. The force due to gravity is just F equals ma, and the mass is given by the density, the area, and the thickness. So the area times the thickness gives us the volume, and then times by the density gives us the mass. The acceleration is g, the acceleration due to gravity. Same time, you've got a pressure P from underneath, so you've got pressure pushing upwards and pressure pushing downwards. And it's the difference in pressure that gives you the net force due to pressure. Remember, the pressure from above has got to be lower than the pressure from below. And at equilibrium, these have to match. So we've got the pressure force and the gravity force. If we rearrange those a little, we can get the rate of change of pressure with depth, and it's a function of the density, which also changes with depth, and the acceleration due to gravity, which also changes with depth. So here's that equation again, and we can basically say as we go to a thinner and thinner slab, so that we can be able to integrate through the whole star, we end up with a differential equation. So we have dp by dr equals minus rho times g. And this actually applies in any situation where there's a pressure-gravity balance. So in our atmosphere, this applies. In the ocean, this applies. Now let's just consider the ideal gas law. I want to briefly go over one little thing just to make sure that we all understand what the letters mean. In the classic ideal gas law, we have PV equals nRT, where we have pressure, volume, the number of moles of gas that we have, the universal gas constant, and the temperature. Now, I'm going to introduce Avogadro's number here. I'm sure you all know it, 6 times 10 to the 23. This is the number of particles in a mole. And so the total number of particles that we have is the number of moles n times the number of particles in a mole. So that's our total number of particles. So now we can put in the value of n, the number of moles of gas, in terms of the total number of particles. There's also a different constant, which is this universal gas constant divided by Avogadro's number, and that gives us the Boltzmann constant K. So we can replace that, that R and NA with a K, so now we've got PV equals N total KT. But if we take N total dividing by the volume, so I've divided both sides out by the volume, then we get the number density of the particles. So we've got the total number of particles divided by the volume they occupy. That gives us the number density. So now that's the little n. And so now we've got P equals nkt. I just wanted to make sure we're on the same page because people often get mixed up about the universal gas constant R versus the Boltzmann constant K. And this is the relationship between them. So let's assume that our star is an ideal gas. More or less it is. It's not moving at relativistic speeds. It's not degenerate, and so it should behave more or less like an ideal gas. So we've got the ideal gas equation of P equals nkt, but the number density is basically the same as the mass density divided by the mass, where rho is the mass density and m is the mass in that per particle. So now we've got that the pressure is given by rho kt over m, and if we rearrange that, we can get the density in terms of pressure and temperature, and then we've got the mass of the particles and the Boltzmann constant. Now remember, we worked out this equation for hydrostatic equilibrium, so we've put in explicitly over here the gravitational acceleration, and here we've got our density, and so we can now put this in terms of pressure. So remember that we've just worked out that rho equals mp over kt, so we put this in, and I pulled out p so that I can rearrange things, so I can get all my pressures on one side and all my depths or radii on the other side. So now I've got an equation where I have pressure on one side and radii on the other. So now we've got this equation, and remember that gr is just the gm over r squared, so I may go back to using that. And here we go, we've got rid of the gm over r squared, and I'm just going to integrate this. And remember that the gravitational acceleration is going to depend on radius, and we also have an r in here, but all I've done is to integrate. So I've integrated this with respect to p, and I've integrated this with respect to r. And now that I've done that, I can basically put in the limits, and I end up with that the pressure as a function of distance from the center, R0 is usually going to be the center, but it could be some arbitrary point, is given by this equation. So all I've done is to log both sides and put in the limits. And what I get is something that says that my pressure goes down exponentially with distance from the center of the star. This is also true if you apply it to the atmosphere or an ocean. You have that the pressure in the atmosphere goes down exponentially as you go up in altitude. You have that the pressure goes up exponentially as you go down in the ocean. So why is this important? Well, basically, hydrostatic equilibrium is what determines how our star behaves. There's always a tendency to try to find balance. And in models of our stars and how they evolve, it's always a battle between gravity trying to pull the star in and gas pressures trying to expand it. And so understanding that condition means that we can understand how stars behave. In the pre-main sequence, where you've got a big gas cloud, we find that gravity dominates, although the pressure is important in moderating that collapse into a main sequence star. During the main sequence, basically you have hydrostatic equilibrium. It's constantly changing, you're constantly regaining it, but basically it's always in hydrostatic equilibrium. And once you run out of fuel in the core, you have this battle between gravity and pressure, so they tend to change their size a lot. Oh, I don't know why it did that. And that's it for hydrostatic equilibrium. And one of our other movies we'll find out how that applies specifically to the formation of stars.